Hi, welcome back to chemistry. This is Miss Gray, and today we get to work on naming covalent compounds. In our last couple of sections we've been working on the naming of ionic compounds, so now we're going to look at the type of bond that forms when atoms share one or more electrons with each other to form the bond, rather than transferring the electrons. When they share, that leaves each atom with a complete outer shell. So the valence electrons for hydrogen have to get to 2, and for all others they would want to get to 8. Remember the octet rule. Every atom needs 8 electrons. A covalent bond then would form between two nonmetals. Remember in our very first section we talked about ionic versus covalent compounds? Those ionic compounds always started with a metal, except for ammonium substances. So let's look at an example of covalent, where we have two nonmetals bonded together by the sharing of electrons. Here's an example of hydrogen. If we were to show the dot structures for hydrogen, then each of them would have one valence electron, right? Well, we just said that a complete outer shell for hydrogen has 2 electrons total. So if these two partner up, then they can share the electrons, right? So we'll circle the electrons that each hydrogen now has access to because they're being shared. And then we'll shade in what they have in common, and this area here that's shaded in, this is where that bond exists. So it's kind of like showing a Venn diagram. What they're sharing is what overlaps in the middle. Well, what's overlapping here is the orbits of the electrons, and each hydrogen now has access to 2 electrons, so it's particularly stable. Oh, I'm not quite ready for hydrogen yet, and oxygen. What I want to show you now is that if we're sharing one pair of electrons, then the bond is designated with a single line like this, because it's sharing a single pair of electrons. And then we would write the formula for this molecule just like this, H2, to indicate that there are 2 hydrogens in this molecule. So a covalent compound tells us exactly how many atoms of each kind make up a single unit called a molecule. In the next example, hydrogen and oxygen, then we'll show their dot diagrams. Here's the 1 electron for hydrogen, and then the oxygen gets to have 6 valence electrons, so we show 6 dots. So for us to form a bond here, we have to take that electron from the hydrogen and move it down into a bond. But here's the trouble. Oxygen still has another electron that needs a partner. So what do? Well, let's just bring in another hydrogen. There it is. And so if that hydrogen can bring 1 electron and the other hydrogen can bring 1 electron, then oxygen will have 8 electrons total. That will fulfill the octet rule, and now oxygen's more stable. Hydrogen wants to have access to 2 electrons. So here you can see the sharing of these 2 electrons is what forms a bond between oxygen and the hydrogen on the left. How about the hydrogen on the bottom? What does it need? Well, since it's hydrogen, it needs 2 electrons. So if it shares the electrons with oxygen, then it also has access to these 2 electrons, so we shade that in. That's where our bond exists. So let's show this, whoops, sorry about that. Let's show this as a molecular structure. A single line will represent the sharing of the electrons. So oxygen is sharing with 2 hydrogens, but then there's these other electrons here that are not being shared. Well, they didn't go away, so we still have to draw those in as dots to indicate that those are unshared pairs of electrons. And then how do we write this formula? How could we show the number of hydrogens to the number of oxygens? We start with the one on the left side of the periodic table, so H comes first, and there's 2 of those, and then there's 1 oxygen, and you're all familiar with this compound, right? H2O. By the way, this comes from Bonding Basics. I want to show you where that is in your packet, because now if you haven't already found it, you need to go back to that packet. Page 4 is where it starts. Okay, so here's your Unit 5 packet. We want to scroll down to page 4 where it says Bonding Basics. Here you are. And we've already completed section A and section B about ionic bonds. So continue on to the next page. And on page 5 in section C, you'll find the part on covalent bonds. So we filled in the first 3 blanks already about how the bonds form. And then we did example C1 and C2, hydrogen with hydrogen and hydrogen with oxygen. So push pause now if you need to and go back to that part of your packet and fill in these notes. We're going to finish up by doing the rest of those examples, and then you'll be done with that activity. You can check it off. Great, so then let's continue on. Let's look at example 9, chlorine and chlorine. So I need my pen back. I'm going to show one chlorine in one color and the other chlorine in another so that we can tell the difference between the two. Remember, everything that's a halogen has the same number of valence electrons, 7. 7 steps across from left to right on the periodic table. So here's my 2 chlorines. Our rule is every atom needs 8 electrons and every electron needs a partner. So here I have an electron without a partner, and here I have an electron without a partner. So in our bond we'll show them moving closer together. So I'm going to show how the dots now are being equally shared between the two. Since they're the same type of atom, there's no reason to suspect they would share unequally. So now the electrons are in between. I'm going to circle the location of these bonds. So here this chlorine gets access to these 8 electrons. See that? 2, 4, 6, 8. Then this chlorine gets access to 8 electrons, and they're sharing the 2 in the middle. So that's a bond that we call a single bond because they share only one pair. So we use a line to show which ones are in the bond, but then we would draw the rest of the unshared electrons as dots because they're still there. They're still around the atoms. They're just not in a bond. So if I can get that dot to stay, there we go. There's our chlorine. And the formula for this is simply Cl2. It's a molecule made up of 2 chlorine atoms. Now let's look at another one, oxygen. And oxygen is going to be a little trickier to get the oxygens to play nice. You see, oxygen has 6 valence electrons. So when I put these 2 next to one another, then I can have partners automatically, but then these 2 need partners too. So covalent bonds can form by sharing more than one pair. If we're going to share 2 pairs of electrons, you know what? Let me draw it as dots. So this oxygen brings 2 pairs and then keeps these for itself. Then this oxygen has these 2 pairs here and here, and it's going to keep some to itself. And so then what you see here is that we're sharing 2 pairs of electrons, these ones and these ones, so that every electron can have a partner. And so this is called a double bond. And we would show its molecular structure just like this with the electrons that are not in the bond still drawn in as dots. And we write the formula simply O2. Let me show you which ones are being shared with our little diagram. So this oxygen here has access to 8 electrons. There's 2, 4, 6, 8. So it has its octet rule met by sharing. Then this oxygen has access to 8 electrons. 2, 4, 6, 8. So everybody's happy, right? Every electron gets to have a partner, and every atom has 8 electrons. Let's show what happens when carbon, with its 4 valence electrons, bonds with oxygen that has 6 valence electrons. So we know every electron wants to have a partner, and every atom wants to have 8 electrons. So let's get our valence electrons drawn in first, and then we'll start pairing them up. In fact, I found partners for 2 of them already. Now what do we do? I've got some electrons with no partner. So it looks like I could partner these 2 up, right? And I could, let's see, partner these 2? Sure, because we can make double bonds here. So let me redraw the structure for us. We have carbon that's now sharing 2 electrons with the oxygen on the right. And then it's sharing 2 electrons with the oxygen on the left. So there's the other 2 electrons from carbon, and then here's the ones from the oxygen. Alright, so now what we see here is the sharing occurring right here, and then here and here. So double bonds in the carbon dioxide molecule. So what do we have? 8 electrons for this carbon, and 8 electrons, I said carbon, for those oxygens. 2, 4, 6, 8. Carbon also needs access to 8 electrons to make it happy. So we're sharing right in here covalent bonds that are double bonds. So here's our structure. And I'm going to space out those unbonded pairs of electrons because free electrons that don't squish together in a bond, they tend to take up more space, and so I'm going to space them out a little bit farther. How do we write the formula for this one? We have 1 carbon, 2 oxygens. That's pretty simple, it's just CO2. Okay, we have one more, and this one's going to be easy. Carbon has 4 valence electrons, so each of those electrons needs to have a partner. And, lucky enough, hydrogen happens to have 1 electron to bring, so if we put 4 hydrogens, and they each bring an electron in, then every electron is going to get to have a partner. Hydrogen likes to have 2 electrons, and carbon has got to have 8 electrons. So each hydrogen now has access to 2 electrons, since it's formed a bond with carbon, and then carbon gets to have access to all 8 of these electrons around it. So that's pretty nifty. We made 4 single bonds here. So in its molecular structure, it would look like this. Straight lines for every single bond. And that's a substance known as methane. It's the stuff in the Bunsen burner. So we write the formula with 1 carbon and 4 hydrogens like this, CH4. That's it. It's that easy. So the bonding basics now you're done with, but there's an extra challenge at the end. I'd like to see you give that a try, please. Now let's look at how to name covalent compounds. It's still one of the easiest things you're going to have to do this semester. So naming covalent compounds, we're going to change the ending to IDE. Just like we did before, IDE is going to be the ending of all of our substances. And then we're going to use prefixes for each element in the bond. So by prefixes, I mean these Latin and Greek terms, where 1 is mono and 2 is di and 3 is tri and so on. So the prefix in this case refers to the number of atoms, not to the charge. Remember when we were naming elements that were, when we were naming ionic compounds where the metals had more than one type of charge, we used a Roman numeral to tell us what the charge was. But in this case, we use a prefix to tell us the number of atoms, not what kind of atom it is. So for instance, N2O4, we would use the 2 to say how many nitrogens. So we call this di-nitrogen. And then what's the prefix for 4? We have 4 oxygens, so I'm going to call that tetra, and then change the ending so it's not oxygen, it's tetraoxide. And that's it. Does that seem simple enough? Here's a prefix. There's one exception. For the first element, if there's only one of them, we drop the prefix mono, like carbon monoxide or carbon dioxide. We don't call it monocarbon, we just call it carbon dioxide, because then the mono becomes redundant. The first vowel is also often dropped to avoid combinations of the double O or the AO, because that gets a little bit confusing. So we would call this carbon monoxide, not carbon monoxide. So we would drop the first vowel so that we don't have goofy combinations like that. Here's another example. Tetraphosphorus deoxide, we drop the A, and we don't drop the vowel in combinations of I-O. We keep the I and the O so that our pronunciation makes more sense. So in sulfur dioxide, keep the I. Wow, we wouldn't be calling that sulfur dioxide, just dioxide. Keep the I, but drop an extra O or an extra A to help with pronunciation. So right up here, dinitrogen tetroxide, we drop the A. So it's just tetroxide. Easier to pronounce that way. Example is, name the following compounds. Well, we already have the names on the screen. So let's try writing the formulas from these. We're going to go backwards. So carbon has the symbol C, and chlorine has the symbol Cl. And the prefixes will tell me how many of each to use. And it doesn't say monocarbon, but that would be redundant, right? We know carbon is just one carbon. Tetra is 4, so I need, for carbon tetrachloride, CCl4. The next one has diphosphorus trioxide. Remember, di is 2, so I need 2 phosphorus atoms. And how many oxygens? Tri stands for 3, so P2O3. And then the next one is iodine heptafluoride. Iodine is I, and then fluorine is F, and hepta stands for 7, so IF7. There we go, iodine heptafluoride. And there's the formulas. Did we do them all right? Of course we did, because I'm an expert at this. All right, well, here's how I did it. The first thing that we do when we're writing formulas from the names is we identify the element involved in this type of compound. And then we use the prefix to write the formula. Pretty simple, right? So here's some examples. Nitrogen dioxide, di stands for 2. So with my nitrogen, I'm going to need 2 oxygens. The next one says dinitrogen trioxide. So di means 2 nitrogens, and then tri means 3 oxygens. So 2 nitrogens with 3 oxygens. Oh, here's one, tetra, phosphorus. Tetra is 4, so 4 phosphoruses, and then decoxide, deca is 10, so I need 10 oxygens with my phosphorus. Finally, I have xenon tetrafluoride, one of the only compounds that can be made with noble gases. So I have my xenon Xe, and then how many fluorines? Tetra stands for 4. There we go. That's it. Okay, now here's your warning. I know this seems really simple and easy, and it is, but a common mistake after viewing this podcast is for students to then try using this system for ionic compounds. This naming system works for covalent compounds. You're going to have to decide whether the compound you're naming is ionic or covalent before trying to name it or write its formula. Remember, ionic compounds start with metals, and covalent compounds start with nonmetals. So pay attention and decide what you're naming. For example, Fe2O3 is called ferric oxide or iron 3 oxide. It starts with a metal, so this is ionic. We could not name it di-iron trioxide because it's not covalent. So we can't do it this way. Oh, and here's another one. NH3 you'll see quite a lot in this class. This has a special name already. Its name is ammonia. So if you call it nitrogen trihydride, it is correct, technically speaking, but this substance already has a name, and we all know it as ammonia, so you'll just have to memorize this one. It's kind of like H2O. you already know that that one's water. You're going to have to memorize this one as ammonia. So if you name it nitrogen trihydride, you're going to get the points for naming it correctly. But I'm going to call it ammonia, and you'll be really confused if you don't know that ammonia is this stuff, NH3. All right, well, that's it for naming covalent compounds. See you later, guys.